Hi, so welcome to the fifth day of this series on perspectives in mathematical sciences. So as we said yesterday, we have the good fortune to have not just established senior researchers talking here, but also some younger researchers who have some connection with CMI, and today is no exception. So over to you, KV, you can introduce the issue.
Yes. Yeah. So Visu graduated with a BSc in mathematics and computer science at CMI. He completed in 2013. He did his PhD in 2018 at the University of Michigan. He worked with Professor Harm Derksen. His PhD work is really excellent, fantastic work. Then he did a postdoctoral position at IAS Princeton, where he was mentored by Professor Avi Wigderson, our first speaker, and briefly also at University of Melbourne. So he is currently a researcher at Radix Trading. Visu's primary interests are in invariant theory, representation theory, and computational complexity. As he says, he likes to develop and use tools from abstract algebraic subjects to tackle problems in tensors, complexity, and other areas of theoretical computer science. Yeah, so Visu will be talking today about interactions between invariant theory and complexity theory. Yeah, over to you, Visu.
Thank you, Kerry, for the introduction. So I've gone through a journey in mathematics since for the past decade, which is when I consider my mathematical career starting, is when I stepped into CMI, and it's transformed me in a way. I started off with certain goals in mind, and then they kept transforming and transforming and transforming, and I ended up somewhere else by the end of the decade. But what I really want to tell you is my view of a story that's also been developing over the last decade. Maybe there's some parts of it that have been developed a couple of decades earlier, but I want to tell you my view of a subject that's showed up mostly in the past decade. And so I titled my talk as Interactions between Invariant Theory and Complexity. So a bit of background about me is I grew up in CMI mostly wanting to do algebra, and I still want to do algebra. And it turns out that algebra you can find in places that you don't expect. One of the places that you can find it unexpectedly is complexity theory. And so I want to tell you how you might find algebra in complexity theory and how I went about finding it and so on. So let me start by just saying, what is invariant theory? In a very, very brief sentence. And I'm going to be a little liberal in what I mean by invariant theory to include representation theory. So invariant theory I like to think of as the study of symmetries. And symmetries to me, for most of my life, mean group actions. Symmetries mean different things to different people, but to most algebraists, symmetries would mean a group action. So that's the first subject that's going to play a role here. And the second subject that's going to play a role here is complexity. And the way I like to think of complexity is that I think it's the study of computational models. And in particular, how powerful they are and what their limitations are. Okay. And so what I want to tell you about today is how do these two interact? And one of the things that actually surprises me a lot as I see more and more mathematicians and computer scientists of all kinds is people can take different views to the same subject, and they can go from being very, very concrete to being a very, very high level perspective without looking at the details. And so I want to emphasize that there are two pretty, it's all the same story that I'm going to tell you, but you can take a very concrete viewpoint and try and establish and understand why these two subjects interact, or you can take a higher level view. And both ways will tell you why they interact, but I'm going to try and go through the concrete approach so that everybody can sort of see for themselves in the nuts and bolts of it why these two subjects can possibly interact. And then with some time left, I might give you a better idea of why they should interact, which is what a higher level interaction goal for you to understand would be. So I'm going to start with some basic problems. These are going to sound like high school problems. So I'll start with this problem called polynomial identity testing. And it's always abbreviated as PIT. So this problem is basically says decide if a given polynomial expression simplifies to 0. Okay, and I want you to think of this problem from an algorithmic perspective. So somebody hands you a polynomial expression. Does it simplify to 0 or not? This is actually something that you do in high school, right? They give you these polynomial identities and they want you to prove them, which is the same thing as saying check whether it simplifies to 0 or not. So an example of something is things that we really know. A plus b into a plus b minus a times a minus 2 times a times b minus b times b. This we know is 0, but then some other expressions that you give may not be 0. And something like this, you can sort of expand out, check it, fine. But what if I gave you an expression that was 10 pages long? Then you'd really want to run it through a computer. And so you need to tell the computer what to do. And then the questions that sort of come up naturally is what happens to be in the study of complexity theory that I said. You want to try and understand algorithms, power, limitations of how hard or easy it is to compute these things and simplify these things and so on. Okay, so let me give you a very simple algorithm for this. And it's called plug-in random numbers. Okay, and the idea is that if your expression was actually 0, then no matter what numbers you plug in, you will always get 0. And if your expression is non-zero, doesn't simplify to 0, then when you plug in random numbers, then with high probability you'll get a non-zero value when you evaluate it. And it's always easier to evaluate because if you plug in numbers for a and b, then you can simplify it by just evaluating all those arithmetic operations quickly. And that's not so hard to do, but it's harder to do on a symbolic level. So you plug in these random numbers and you check it, and with high probability you get your answer. This is what's called a randomized algorithm. But of course, complexity theory sometimes wants you, and for very good reasons, we want to find a deterministic algorithm that is polynomial time. And I don't want to be very rigorous about what polynomial time is in this context. It is polynomial in the most obvious, in the most reasonable sense that you might expect. So the question is, can we come up with a deterministic polynomial time algorithm? And the answer is kind of complicated, but we may or may not be able to do it. But it was shown by Cabanets and Impagliazzo in 2004 maybe, that if you are able to come up with such a polynomial time algorithm, then you approximately prove p not equal to np. And I won't expand upon what this approximately is because it's not so relevant and maybe a bit technical. Okay, that's a good reason to understand algorithmically something that we all do in high school. What I'm going to do now is I'm going to step it up a notch, and I'm going to change the problem a little bit. It's called non-commutative rational identity testing. Okay, which I'm going to abbreviate to RIT throughout this talk. So it's the same question, except now instead of commutative polynomials, you have these rational expressions, and you want the variables to not commute. So I'll give you an example: a plus ab inverse a whole inverse plus a plus b inverse minus a inverse. And I ask you, remember that a and b do not commute. Does such an expression simplify to 0 or not? And now this is on the face of it, at least, looks like a harder problem. And maybe this is a point where I pause for the audience to tell me if they know whether this simplifies to 0 or not. I'll just think about it for a second or 2 minutes. Anyway, So it's not so clear if you start trying to think about it. How exactly do you go about simplifying these things? And there's a couple of things that are actually issues that I can point out. First is, or actually maybe the most important issue really is to point out is this feature of what's called nested inverses. So for example, you have this inverse here, and it's in some big expression, and the whole thing is nested inside another inverse. So this is the kind of thing, if you just try to simplify naively by hand, you don't know exactly where to start. And here's something for you. If you get bored in my talk, which is very much possible, try and solve this. Try and see if this simplifies to 0 or not. Okay? That's a good exercise and very instructive. And of course, if you can't do it, then at the end of the talk, maybe I can tell you how to do these things a little bit. Okay. So, give me a second. So in this case, the question that we really have to start with is there any algorithm whatsoever? So remember, I mean, when you want to try and give this to a computer, you want to make sure that you're not trying to spot patterns here and there in some funny way depending upon what the example given to you is. You need an algorithm that works blindly just by looking at the input and just passing it in a more mechanical way. Okay. So the fact that you could have solved it in this case, I think somebody already did. That's good. The fact that you could have solved it in this case with by spotting certain patterns doesn't mean you could have done it in general. In particular, if I give you something that was a page long, I don't know anybody who would know where to start. Okay, cool. So we have this problem that looks on the nose harder than this PIT problem that I told you before. Okay. But now what I want to do next is I want to sort of unify both of these problems. So there's a certain construction, and it starts with any expression. It could be rational, yeah, it's a rational expression or a polynomial expression, doesn't matter. And there's a construction which takes you down to what's called a linear matrix. Okay? And this construction in the commutative case is due to Valiant, and in the non-commutative case it's due to Hughes and Wigderson. And what does this thing have? I mean, the property of this construction is that you start with an expression, let me call this f, and you will come down to this linear matrix LF, and somehow whether f is 0 or not, or let's just say f not equal to 0, will be dependent upon whether LF is full rank or not. So let me give the example first, and then I will talk a little bit more about the details. So the example that I'm going to do is I'm going to take this expression AB minus BA. Okay, and through this magical construction that I'm not going to tell you about, you will end up with this matrix, or something close to this, but it's good enough for the illustration of the idea. Okay. And this is what this is the linear matrix. So why is this called a linear matrix? It's because every entry in this matrix is a linear function in some variables a and b, and of course you allowed some constants. So why exactly is this linear matrix related to this function? To do this, I have to do Gaussian elimination, because I'm saying something about the rank of this matrix, right? So let me do the Gaussian elimination. And I will do Gaussian elimination in the most general form possible. So I won't assume whether A and B are commutative, non-commutative. I'll just assume they're non-commutative. And if they're commutative, it's no big deal. So I want to get rid of this minus B and minus A in the bottom. So I'm going to multiply the first row with A and add, and the second row with B and subtract. So the third row is going to go to the third row plus A times the first row minus B times the second row. Okay. So what is this going to do? This is not going to change the first two rows. And in the last row, because I've subtracted B times the second row, this B gets killed. because I've added A times the first row, this A gets killed. And if you see closely what happens here, I will get an A times B minus B times A. Okay. And then, because I have these columns with these pivot ones, I can get rid of these B and A. Okay, so I won't tell you what those transformations are. You can write them down very easily. And you end up with a matrix that looks like this. So what you ended up with is essentially almost like an identity matrix or a permutation matrix, the ones that kind of moved out. And in this one, there's just one non-trivial entry here that shows up in this matrix, and that is the original expression that you started with. And so, what does this mean? This basically means the rank of this matrix is either full or one less than full. And what it is depends on exactly whether this expression is 0 or non-zero in your context. I hope that construction is sort of clear. I can make this a little bit more precise if you like, but it's maybe not so important. But I will make something a little bit more precise. So the only thing is, I said, okay. So what do I need to really make precise? So I said I want to know whether the rank of LF is full or not. And the question that you might ask me is, what do you mean by the rank? It's sometimes a little bit clear from the example, or you can maybe extract it out, but I will be a little bit precise about it. So in the commutative case, we will call it the commutative rank, and this is basically the rank over the function field where you add in these variables. So it's a function field over two variables. So that's about as, so I want you to think of this as, so this is the function field, but I do want to think of it as sort of the free field over C, free field of two variables over C. That's the freest field that you can get if you wanted to extend C by two extra variables or two extra things. Okay. Now in the non-commutative case, we will call it the non-commutative rank, and this is going to be the rank over what's called the free skew field. And this is precisely analogous to this function field in the non-commutative case. So you start with the complex numbers, you throw in two variables, and you throw in no additional relations, and you end up with what's a skew field, because you're now in a non-commutative setting, and that's what's called the free skew field. And that, by the way, this is one way you can construct the function field, is just take complex numbers, throw in two variables, ask for no more relations than absolutely necessary, and what you'll end up with is the function field with two variables. Okay, but I do want you to remember these notions of commutative rank and non-commutative rank, and that so what I really want you to remember is I can take linear matrices and I can ask for commutative rank and I can ask for non-commutative rank, and these are going to be crucial notions for this talk at least. Okay, so another way to write a linear matrix, for example, we had this linear matrix LF to be 0, 1, minus 1, 0, BA minus B minus A 0, right? So I want to write this matrix as x0 plus A times x1 plus B times x2, where xi are 3 by 3 matrices with complex numbers, let's say. Okay, so how would you do this? X0 would just be the one, would just be the constant part of it. X1, so that's what x0 would be. X1 would just be this guy. I'll just pull out the B part. Sorry, this would be x2 actually. Sorry, let me correct that. 0, 0, 1, minus 1, 0, 0, 0. And x2 would be this guy. Okay, so in general, linear matrix is something that looks like x0 plus t1 x1 plus tmxm, where ti are variables and xi are matrices in the with entries in the underlying field. Of course, you can have the variations where you can change this underlying field from complex numbers to something in positive characteristic and so on, but let me just stick to it for the purpose of this talk, or at least for now. Okay. So this is basically what a linear matrix is. And is that clear? Any questions so far? Because now I'm going to tell you a theorem that's going to now push me into invariant theory. Okay. By the way, if you have any questions, just put them out in the chat and I will get to it when I get a break. So here's an important result, and I don't know who exactly to attribute this to, so I won't attribute it to anyone, but it's also kind of a historical result, I think. Yes. Put together many results that people know. So you have a linear matrix, and the following are equivalent. So the first is that the non-commutative rank is not full. And the second is that there exist subspaces V and W. Okay, so let me be precise here. Ti are variables, xi in n by n matrices over the complex numbers. So there exist subspaces with the dimension of V greater than dimension of W. So these are both subspaces of Cn. Such that for all I, xi will carry V into W. So it's sort of every one of these matrices will shrink a larger subspace into a smaller one. And that condition is the same thing as the non-commutative rank being not full. An equivalent way to say that, and this is perhaps something that people who like explicit matrices and bases and so on might appreciate better, is there exists changes of bases p and q such that for all I, p xi q will look in this form, where this is a block of zeros. Let me write this down as a block of zeros of alpha and beta, where alpha plus beta is larger than n being the size of these matrices. And so if you think of it, by the way, maybe this is an exercise I leave to you, to see that 2 and 3 are exactly the same condition, in one being, I would say it's the second one is what you would like if you grew up an algebraist and never wanted to touch bases. And the third one is what you would like if you grew up maybe as a computer scientist and always wanted to find bases. So these are okay. They all seem kind of concrete. And then the last condition is something that is going to throw us into the world of invariant theory, is that this tuple of matrices is in the null cone for the left-right action. I introduced two new terms here. One is the null cone, one is the left-right action, and I'm going to come and tell you about what these things are. But this equivalence is basically what allows us to relate non-commutative rank to some notion called the null cone for some action called the left-right action, and this is all things in invariant theory. Okay, so these guys here are invariant theory. And so what I'm about to tell you now is we start with all these complexity problems on identity testing and so on and so on, and then we morph them into problems on ranks. And I think that is something that I want to sort of emphasize, is once you come to this land of having matrices and ranks, then you suddenly open yourself up to the possibility of using a lot more mathematical ideas than you would when you still looked at it as identity testing problems. Just because matrices and ranks appear all over mathematics in many subjects. And invariant theory is one of them, but as you will see, there are other subjects too that can help when you take up a perspective that includes matrices and ranks in a very, very natural and sort of nice way. Okay. So what I will do first is, instead of telling you what the left-right action is, I will tell you a little bit about the null cone. Okay. So this is what's going to bring us into invariant theory. And By the way, the way I plan this talk is I don't intend to go deep into technical details. So I'm going to try and be kind of light. I'm going to ignore certain assumptions and so on, which is not going to be so crucial for this talk. So the setting is again going to be a group that's going to act on some vector space. This is also called a representation. Depending upon how you like to call it, a linear action, a representation, group action, whatever we like. And the null cone, I'm going to give two definitions of the null cone. So the first one is that the null cone is a set of vectors such that 0 is in the orbit closure. Okay, so let me explain this a little bit. What is this orbit? So this orbit, let me go back to black. So this orbit is a set of all points that you can get to by applying different elements of the group. So you start with this vector v, you apply all the elements of the group and you get some subset. And now you want to see if 0 is a limit point of that or not. And if 0 is a limit point, then the vector that you started with is in the null cone. And if 0 is not a limit point, then that vector is not in the null cone. Great. Now here's a different kind of definition, and maybe something that looks very different, is it's the vanishing set of non-constant, homogeneous, invariant polynomials. Okay. So we want non-constant polynomials because you never want to take the vanishing set of constant polynomial. You get nothing useful with that. Homogeneous, ignore it for now. It's not the most important part of it. But the most important part of it is invariant polynomials. So the null cone, which I told you, is something about taking orbits and seeing whether the limit point, whether 0 is a limit point of that or not. That condition somehow is captured by the vanishing of certain polynomials. So the 0 locus of a collection of interesting polynomials that we call invariant polynomials. So what is an invariant polynomial? So a polynomial on this vector space. By the way, a polynomial in a vector space isn't a great thing. If you think of the vector space as c to the n, then you just take a polynomial in n variables. You can evaluate it at any point in this vector, in this vector space. And this set of and the collection of polynomials we usually denote by c brackets v. It's an algebraic notation, not a big deal. But this is an invariant polynomial if f of gv is f of v for all g in g and v in v. This just means that whether you evaluate this polynomial at some vector v or whether you evaluate it after applying some group element, you should get the same value. That is what it means to be invariant. And another way to say this, and one that I actually like saying many times, is this condition is the same thing as saying f is constant along orbits. And if you think of it, if it's constant along orbits, and these are continuous functions because they're polynomials, and so they're constant along orbit closures. So you can see if you have a homogeneous polynomial, it's always going to take the value 0 and 0. And if it's invariant, it's going to take the same value on the orbits as well as the orbit closures. So if you have an invariant homogeneous polynomial and you have this vector v that's in the null cone, it must take the same value as this homogeneous invariant polynomial takes on the point 0, which it's a homogeneous polynomial, so it always takes 0. And that gives you one inclusion here as to why one of these sets is included in the other. It's a fairly simple argument. And the converse is not going to be so easy because there's a couple of technical hypotheses I have to attach to the group and the representation for it to work. So you won't be able to do it without knowing what those technical things are, but it's basically a rational representation of a reductive group. And most likely, if you already know this, then you probably already know how to get this result or know where to look it up. Okay, so we have these two definitions. And why am I trying to tell you two definitions? I'm trying to tell you two definitions because they're going to play, what shall I say, complementary roles in this story going forward. I'm going to take the second approach for now, and I'll come back to the first. I'll come back to the first definition. So before I do that, let me tell you what this left-right action is. Because if you remember, this non-commutative rank business is something that was about this left-right action and the null cone for it. So let's figure out what this left-right action is. And it's not so complicated. The group here is SLN cross SLN. and the vector space is m tuples of n by n matrices, and the action is kind of quite plain. They just act on every matrix, one on the left, one on the right. So PXM Q inverse. And for those of you who like or are aware of quivers, I know there's a course on quivers that happened recently. M matrices you can think of as the representations of a quiver with two vertices and m arrows. So a quiver is just like this director graph, so this picture that I drew, and a representation of it is you stick a vector space at the vertices and you put a linear map in between. So if I stick n-dimensional vertices, n-dimensional vector spaces of these two vertices, then any linear map is basically an n by n matrix, and if I have m of them, m arrows, then it's a collection of m matrices. And changing bases will change bases simultaneously, sort of like how this formula will tell you. And that's the connection to quivers, which is very helpful, but let me not go there. Okay, so we're interested in null cone for the left-right action, right? And so this we know is equal to the vanishing of some words in here, invariant polynomials. So what are these invariant polynomials? Okay, so any guesses for any one particular polynomial that you can tell me is invariant? There are some that you really know, and it just takes a minute to guess, and maybe I'm going to wait for, I'll count till 10. Maybe someone could tell me quickly one invariant here. Okay, well, I think people are maybe a bit shy, or maybe already know, so they don't want to tell. Okay, so here's an example of invariance. Okay, so let's just write some examples of invariance. And this is a good exercise to understand what I really mean by invariance here. I want to look at the determinant of x1. And I want to say it's invariant because whether I evaluate it on x1 or if I apply some group element, then I would have to evaluate determinant of px1q inverse. And those two determinants are going to be the same because p and q are in SLN. Okay. And now if you think about it a little bit more, you can actually realize that you don't have to take just any one matrix. You can take sort of a linear combination of these matrices. That is also an invariant. And then you might ask yourself, is this all? And if this were all, we'd be singing a very different tune about polynomial identity testing. And again, if you're bored, you might wonder what exactly I mean by that. But then the point is that these are not all the invariants. So here's an example of another invariant that you might like. x1, x2, x3, x4. So I take this 2 by 2 block matrix and I stick an x1, x2, x3, x4 there. Okay, and you look at its determinant. Well, there's one thing that's common about these is I always seem to want to write a determinant there. That's not going to change. But now I'm being a little bit more bolder. Instead of taking linear combinations, I'm trying to do tilings and so on. So in general, you can look at some d by d tiling. I'll just call them tilings because I don't have a better name. So d by d tiling, and you can take the determinant of such a tiling where every entry is a linear combination of the xi's. And not just are these examples of invariance, but this is all the homogeneous invariance. I say all because it's a spanning set. Of course, you can take a linear combination of those invariants and they will still be invariant. But in some sense, these are all. Great. So if we step back for a second, to get to hold of whether non-commutative rank of a linear matrix is full or not, you have this tuple of matrices. You want to know whether it's in the null cone or not for the left-right action, which is the same thing as saying, is it in the vanishing set of homogeneous invariant polynomials? And I told you what the homogeneous invariant polynomials are. So the algorithmic question becomes, I give you a tuple of matrices. Can you, or does there exist some tiling of, some d by d tiling for some d, where each one of these blocks is a linear combinations of the xi's, so that this entire big thing happens to have a non-zero determinant. Okay. So let me write that down precisely. So here's the problem at hand is, or maybe I just write it down as a criterion. So x1 to xm is in the null cone, is not in the null cone actually, if and only if there exists a tiling for some d. Such that determinant is not zero. Okay, so these are all linear combinations of xi's. Very concrete problem, very concrete problem. And so here's where I tell you a theorem of mine with Harm Derksen, and this is something that I proved somewhere in the middle of my PhD, and which I was really happy about, because it got my research career going. And what I prove is that x1 to xm is not in the null cone if and only if determinant of, or maybe let me say this, if and only if there exists a full rank tiling. Full rank is saying the determinant is non-zero for d equal to n minus 1. Okay, so here's what I have to tell you now. I told you the story a little bit in reverse order. So what happened first is Ivanios, Kyav, and KV Subramaniam, who's in the audience right now. So these people worked on this problem for a long time, and they proved many interesting results about these tilings and how you can go between, and the possible ranks that these tilings can have and so on. And one day I came back to CMI in the summer, and my advisor had told me about this problem, and I was thinking about it from a completely different perspective, and I was getting nowhere. And then I went and talked to KV, and then he said, oh, we have this preprint that we're going to put up soon, and he's like sent me an advanced copy. And I looked at it, and I realized that there's this little trick that you could use, and this little trick combined with all these amazing techniques that these people had brought up would give us a great result. And that's the little trick that I used to put the theorem down there. So when we combine it with all the other results that these three people proved, they realized again that this was maybe the last missing link in giving a polynomial time algorithm for this null cone membership. Or maybe I'll call it let's call it null cone membership for left-right action, which is equivalent to determining if non-commutative rank is full or not, which again is equivalent to this non-commutative rational identity testing problem. So again, I'll pull you back to the beginning, where we started with this commutative case where it was these polynomial identities that we all studied in high school, and we don't know how to give a polynomial time algorithm for it. Then I said I'll step it up a notch, and I started introducing rational expressions and non-commutative variables and so on, and we suddenly had no idea how to do these things. And after a long winded story that went through recharacterizing it in many ways and pulling more and more symmetries out of it, and finally into invariant theory and tilings of matrices and so on, and a lot of results about these things that I haven't told you about and I won't tell you about, what you end up with is a polynomial time algorithm for this seemingly harder problem. Okay.
Nice.
Okay. So that's the story that really that I was really happy about for several years until you get bored of it. But I hope it's still interesting for everybody else.
Yeah.
So here's what I want to say is, if you look at these tilings, any such tiling, this d by d tiling is like a dn by dn matrix, and so the determinant is a polynomial of degree d times n. And the language we sort of proved our result in is to say that we have a polynomial degree bound on invariant polynomials needed to catch the to capture the null cone. So in this case, if you only have to look at tilings of n minus 1 by n, n minus 1 by n minus 1 tilings, then these matrices are about n squared big, And so this means that, you only have to look at polynomials of degree about n squared if you just want to capture the null cone. So that's the viewpoint that I want to just put. Point of the theorem in the previous page is that polynomial degree invariants suffice to capture null cone for the left-right action. So that's the viewpoint that we have. And why I want to put this viewpoint across is because then it makes me, then it lets me help you understand better the next two sort of theorems, which I put in red because they're supposed to be bad theorems in some sense. When I say bad theorems, I mean theorems that we don't like because they're sort of bad news, but they're not quite barrier results. So the first result I'm going to tell you is I'm going to go to what looks like the next step from the left-right action. So instead of 2 SLNs, I take a 3 SLN, and the matrices then become sort of tensors. 3 tensors, and I take m copies of this. So for this action, what we prove is we show that you need exponential degree invariance to capture the null cone. And now this is kind of problematic because, for example, if you wanted to take the determinant of an exponentially sized matrix, that's a hard thing to compute. That you're not going to be able to do in polynomial time. Okay. So that tells you that it's a little bit difficult. At the same time, the fact that you have exponential degree polynomials that you have to compute is not necessarily a barrier, because you can compute with polynomial size circuits, polynomials, with like small circuits, you can compute exponential degree polynomials. Okay? So it's not quite a barrier. It is bad news, but it is the state of art. And by the way, this is actually the action that we find kind of tantalizing and at sort of at the, so this is basically the action where we're stuck. So we don't know how to do anything harder than this, anything easier than this. We probably know how to do it. And so it's actually kind of an interesting position to be in, where the action that you're actually stuck in is very, very concrete. And it's also being studied by many people from many different perspectives, right? Tensors is a big thing. And then I also want to tell you another result, which there's too many authors, so I'm not going to list them out, but I'll tell you. This is Ankit Garg, Christian Eichenmeyer, myself, Rafael Oliveira, Michael Walter, and Avi Wigderson. And we prove just kind of an interesting result that I can't tell you precisely the formulation, but it's kind of interesting, is we go, instead of 3 copies, we take 4 copies. And of course, we look at the tensor space on 4 tensors. And here the result is that writing down invariance succinctly, actually, let me put it a different way. Any set of generating invariance contains an NP-hard polynomial. Okay, it doesn't mean anything to call a polynomial NP-hard, so I'll put that in quotations, and if you can expect what it means, you'll expect what it means. So that's kind of annoying, because if you were trying to look for a generating set of invariants to try and capture this null cone, it's going to be really bad, because no matter which set of generators that you try to pick, one of them is going to be really, really hard to compute unless P is equal to NP or something like this. Yeah. Okay, so those are a couple of no-go results that I have. And so what I'm going to tell you, though, is I want to go back to this other this other description of the null cone, which was that it's a set of vectors such that 0 is in the orbit closure. Okay, and I want to tell you that I skipped actually a very, very important part of the story. So prior to our results, there was actually another polynomial time algorithm. So there was another polynomial time algorithm for for these problems, for non-commutative rank, or null cone for left-right, or rationality testing, all of these things. And this was by Garg, Gurwitz, Oliveira, and Wigderson. And what they essentially did, and I'll give a really, really brief perspective, is they think of this as an optimization problem. They want to know if the infimum of the norm along the orbit is this equal to 0 or not. And it's kind of the same question as whether 0 is a limit point of the orbit closure or not. Because if it's not a limit point of the orbit closure, then the orbit is sufficiently away from the origin that the infimum of the norms is going to be greater than 0. And if it is a limit point, then of course the infimum is going to hit 0. And so I won't tell you what exactly they did, but but the idea really is that this is an optimization problem. So you want to try and do a gradient descent, maybe that kind of an algorithm, but then you look for convexity. You can't find it because these are not convex problems. And then you find what's called geodesic convexity, and then it all works. But of course, this is still not powerful enough in general. And this is the subject of pretty current state-of-art research, and I will refer you to this 110-page long paper that sort of contains precisely what this method is and everything that you would want to know about. Burgesser, Cole Franks, Garg, Oliveira, Wigderson, and Michael Walter, and this is in Fox 2019. And so this paper explains basically a summary as well as many new results of this kind of an approach that I do want to put forward to contrast. I gave a very algebraic perspective on how I look at these complexity problems, but I also want to emphasize that there is this alternate approach, and very promising approach, which looks for optimization, techniques in optimization. If you think about it, that trying to make these things work is really fundamentally new problems and challenges in optimization, and that could potentially use tools from anything from symplectic geometry to Riemannian geometry to just plain old computer science tricks, algorithmic tricks, and or I don't know, geometric combinatorics. There's many things that you could possibly try and use for these things, and it's all fair game. It's all fair game, and what I think is really interesting is there is some in this subject that actually is an amalgamation of many subjects put together. You can come in from any perspective that you have, any background that you have, and you can contribute to the subject in a concrete and useful way. Okay, and so I have maybe just a couple of minutes left.
And
so
should I just ask you a question? So
yes.
In this context, what do you look at the 4 tensor problem or the 3 tensor problem? One does expect the solution, at least for the null cone one. I mean, what is the feeling? Is it that it is going to be polytime? It's not going to be polytime?
Well, it depends on who you ask whether you believe it or not. But the techniques kind of are stuck in the sense that the quantities that they depend upon, at least the current techniques that we know with geodesic convexity. But I want to say, okay, geodesic convexity is a recent thing. People have only worked on it for a couple of years in terms of this optimization approach. So they only try and do whatever is in great. So far, they've tried to mimic standard techniques from gradient descent without too much innovation, I would say, so far. And those techniques, the kind of quantities that they depend upon, they don't look good for tensors. But if you can come up with some of the more refined techniques in gradient descent, like there are these things like Nesterov's acceleration method or something that people talk about, and those kind of really advanced techniques, if you can make them work in this context, then there's hope. I would say.
Okay.
There's hope.
Okay. Yeah. Thanks.
Okay. So what I want to end with is maybe the high-level perspective. And this is, and I don't like to start with this, although you can start with this if you have the right background, but I will refer to Mulmulay's GCT5 paper. And so what he does is he looks at these things that I like to call orbit problems. So again, you have a group acting on a vector space, and you can ask these kind of questions. You can ask, is 0 in the orbit closure? This is like the null cone membership problem. Okay. you start with this vector space, and let's say V and W are two small vectors in there. You can ask whether the intersection of these orbit closures is empty or not. You can ask whether one of them is in the closure of the other. You can ask whether they're the same orbit, for example. Okay. So these are all things that I like to call orbit problems. And it turns out that for specific instances of specific groups and specific actions and so on, these things actually capture many interesting problems in complexity. For example, graph isomorphism, if you phrase it appropriately, is the last one for the symmetric group acting on matrices in a particular way. And rational identity testing with enough reformulation happens to be a null count problem, which is the first one, and so on. And the other thing that you may have heard of is this permanent versus determinant problem, and that happens to be an orbit closure inclusion problem, which is the third one. And okay, this is all sort of half-filled arrows throughout, but one way to summarize it is summarize Mulmuley's program is that orbit problems are a stepping stone towards P versus NP. Okay, now that's all. Okay, this is what I tell you, and you have to kind of believe me for this talk. But it's a paper that is quite. I would say it's a landmark paper. It's been around for about 8 years now, and it contains many interesting results, many important results, and definitely sets the tone for future research, among other things. Maybe with that, I will stop because I seem to have run a bit out of time.
Lovely talk as usual, Visu. So are there any questions for Visu?
I have a question.
Yeah, go ahead.
Yeah, so is there a reason why we need to look at like 2 tensor, 3 tensor, 4 tensor separate, as in a high level reason, and not have a direct result, something like the K tensor problem for large K?
No, absolutely not. Absolutely not. It just happens that 2 tensors is matrices, something that we know how to work with, and we've been able to wrap our heads around and solve things. And of course, I mean, there's not much difference between 3 tensors or 4 tensors or 5 tensors or 6 tensors.
Yeah.
Just saves me writing space to write 3 tensors.
No, so I was asking like 2 tensors versus K greater than equal to 3 tensors. So you had a separate result for 3 and 4. So yeah.
Yes. Yeah. So it's 2 versus greater than 2. And this is a theme that you will see anytime you come across matrices and tensors. Matrices you're somehow able to manage, and tensors you can't manage yet, or at least you find really weird ways of managing.
So any more questions?
Hi, Visu. I have a question.
Yes.
You said that RIT is equivalent to that non-commutative rank problem, right?
Correct.
One side is obvious that RIT reduces to non-commutative rank, but how is the other direction too?
Well, if you think of non-commutative rank as Gaussian elimination, then you have to solve many RIT problems along the way.
But will there be formulas? Because these RIT problems, like the way Rubes-Wigderson defines a formula, right?
Yes. Yeah,
So,
there will be formulas. When you do Gaussian elimination, you will be doing. No, I think. Okay, I don't mean Gaussian. I don't know. Gaussian elimination means many things, but I mean row and column transformations. And when you do that, you end up with formula-like things. Unless I've got it wrong. Did I get you wrong here? Or is that...
I'm not sure. Is this non-commutative variable? I'm not sure that you'll get a polynomial time reduction to a poly-size formula.
Well, I mean, any row transformation is going to be. Let me think again a little bit. So you start with the rational transformation, you get this. I think it's written down somewhere, but I believe it's the.
Okay, maybe we can think it later. Yeah.
Yes.
Yeah.
I think yeah, you should. I mean, the other result of yours, no, that not everything is PIT. I think that's a beautiful result also.
Yes. Yes. Well, okay. So Upendra sent me a message asking whether I will tell you whether I will tell how to think about Hua's identity,
Okay, the first.
and maybe I will.
Yeah.
Plus A plus B inverse minus A inverse is equal to 0 or not. Okay. So I want to do this, and okay. So now I'm in a bit of a fix because I think I remember how to do it, but if I get into trouble, you can tell me. So first, instead of putting equal to 0, I'm going to take A inverse to the other side. That's okay. And now I want to factor out an A here. So I'm going to write as A times 1 plus B inverse A whole inverse. And then on this side, I want to also factor out an A, but it's going to look like 1 plus A inverse B whole inverse. Okay. Non-commutativity. So A times A inverse B is B. I missed a bracket somewhere. Yeah. So I took this expression inside here and oh God, how do you undo? Maybe you don't undo.
Up. Yeah. This back arrow. Yeah.
Yeah. So I took this expression inside the bracket here and I pulled an A out on the left. Inside this expression also I pulled an A out on the left, but there is no A sticking next to the B, so I have to multiply with an A and A inverse, and I pull out the A and I stick the A inverse there. It's standard, not so bad an argument. So when I have this expression here, okay, so it's non-commutative, so I can write this as 1 plus B inverse A whole inverse times A inverse plus 1 plus A inverse B whole inverse times A inverse. Okay, and then I factor out. I factor this thing out times A inverse, and okay, so remember, this is what I want to prove. So what I really want to prove is I just want to prove
this is 1.
I want to prove that this is equal to 1. Okay, so if I just set X to be B inverse A, I don't care, just relabeling it to make things look clearer. This is 1 plus X inverse plus 1 plus X inverse whole inverse. Okay, so we want to prove this is equal to 1. And I claim this is a commutative thing. Regular commutative identity. And why is this a commutative identity? Because you just have one variable in there. So there's nothing for it to not commute with. And so you could just clear denominators here and check that it works.
Okay. Nice. Any more questions, Visu? No? Okay, so let's thank him for a wonderful talk. Was there nothing in the chat? No, I didn't see. I did see anything in the chat. Sorry.
Yeah, no, there was nothing in the chat.
So there was nothing in the chat. Yeah. So we got it right, but
then he had second thought, so it doesn't
Thank
count.
you.
So I just turn off the recording.
Oh, is it? Oh, I